Hello, you're welcome to my channel. My name is Silo and in this video we're going to find the pi derivative of power functions. So what do you mean by that? Okay, so this is what I mean. We mean the derivative that is the pi order derivative with respect to x of some power function x raised to the power of lambda, where this lambda here is a real number. Good. Okay, but what do we really mean? We usually have some derivative, let's say the derivative with respect to x of some function, we call it the first order derivative. Then for the second order, that is when we differentiate the function twice. That's the second order derivative. And let's say we differentiate the function 3 times, we're going to call that the third order derivative. So that will be the derivative, that is the third order. So what do we mean by pi order? Are we supposed to differentiate the function pi times? Well, how does that make sense given that pi is an irrational number? Okay, it has a decimal part. Good. Okay, so that leads us into what we call fractional derivatives. Alright, so let's see what we can do. So let's start off with what we know already. Now for the integer order derivative, that's what I'm going to call the normal orders. Okay, that's the integer orders. So if you have the integer order derivative of some power function, let's say x raised to the power of n, that's the first order. Okay, where this n here is a positive integer. Okay, this gives us, using the power rule, n into n, that will be, we bring the power down, you write x and then you subtract 1 from the power, right? Good. So for the second order, that is, if we were to differentiate this thing twice, this gives us, well, you bring the n minus 1 power down. That means you're going to have n into n minus 1, okay, times x raised to the power of n minus 2. Good. Let's do that one more time, well, for this order. So that will be the third order derivative of x raised to the power of n. That will give us, well, you bring the n minus 2 power down, that will be n into n minus 1 into n minus 2 x raised to the power of n minus 3. And we can continue, alright? But let's generalize. So let's say that for any order m, where m is at most n, so let's say m is at most n, for any of such order, this is what we're going to have. Okay, x raised to the power of n is, well, notice what we have here. This will be n into n minus 1 into n minus 2, okay, and so on and so forth, up to n minus m minus 1. Okay, m minus 1. Good. Then we put x raised to the power of n minus m. So you notice when the order is 3, it will be x raised to the power of n minus 3, and here will be n minus a number less than the order. So that's what we have. Okay, for each of these, we can rewrite each of these using factorial notations. So for the first one, n is the same thing as n factorial divided by n minus 1 factorial. That is the coefficient. Then we write x raised to the power of n minus 1. Should really be helpful. Then for the second one, this is going to be, well, notice it's n into n minus 1. We can write it as n factorial into n minus 2 factorial. So when you expand the factorial notation, you're going to see this is x raised to the power of n minus 2. So for the third one, what we'll have is, let me put this one. Okay, so now what we'll have is n factorial divided by n minus 3 factorial, right? Good. Okay, x raised to the power of n minus 3. This is n, this is a factorial. Let me write that well. Okay, that's nice. So what would you get for this general order m? This is going to be n factorial, of course, why not, divided by, well, this is going to be this is n minus 3, so this is going to be n minus m. So why is that? Factorial, it's just a generalization of this, x raised to the power of n minus m. Okay, so you notice this is n raised to the power of x raised to the power of n minus 3. This is n minus 3 factorial. So why not? Of course. Okay, so this is what we have. Okay, so we say suppose the order of integration or differentiation, suppose the order is some real number okay, and that is some positive real number alpha, and the power, that is the power of the power function, okay, is some lambda, okay, where lambda is some real number. Good. Okay, so let me put it that way. Good. So suppose we have that. That means we're going to be talking about the derivative, that is the alpha order derivative with respect to x of x raised to the power of lambda. Good. So what would this be? So that is the question now. Well, once we know that, that means we can find such a derivative, then we can get the general result. So let me copy this, and then let's see what we can use it for. Okay, so this is the result that we copied. Now we want to let's get what the alpha order derivative with respect to x, okay, of x raised to the power of some lambda is. Good. Okay, so using this, okay, so this is n factorial, where n is the order, sorry, where n is the integer power, and this m here is the integer order. Now, a case where the order is alpha is not an integer, and then the power is lambda, it's not an integer. Okay, probably not an integer. It's just a real number which integers are included, right? And this alpha, which is the order here, is a positive order. In other words, a positive real number. So every positive real number, including the integers. Okay, all right. So let's see what we can do. Well, you notice that factorial, of course, recall that factorial is only defined for positive integers, or let's say non-negative integers, because 0 factorial is 1 by convention. So since that is the case, how can we put in a random or an arbitrary real number into some function, okay, into some factorial notation? Well, we have to use the generalization of the factorial, which is the gamma function. So the gamma function is defined as this. If you had the gamma function, let's say the gamma of some beta, where beta is some real number, such that the gamma function is defined. Okay, this is going to be the integral from 0 to infinity of, let's see. Okay, let me write gamma of beta plus 1. Good. So this is gamma of beta plus 1. Okay, that is e to the power of negative t times t to the power of beta dt. Good. So this is the definition of the gamma function, and when we have that, okay, we can easily observe, by observation, we notice that gamma of beta plus 1 is the same thing as beta factorial if beta is an integer. But if it is not, we use the gamma function, the gamma notation. We better off with that. And this gamma function is only defined when the input is not a negative integer and it is not 0. So for every other real number except the negative integers and 0, the gamma function is defined for. Okay, great. So with that means we're going to rewrite this. This is the same thing as, if we want to use the gamma notation, that'll be gamma of n plus 1. So you notice that using this right here. Okay, this is n minus m. So we're going to add 1 to the n minus m inside the gamma function. So that will be n minus m. Okay, n minus m. Okay, so we add 1 to that. Factorial. This is x raised to the power of n minus m. Good. So in a case where n is replaced with alpha, and then n is replaced with lambda, we're going to have lambda plus 1 inside the gamma function divided by gamma of, that will be lambda minus alpha plus 1. Good. Then x raised to the power of lambda minus alpha. Okay, that's nice. So this right here gives us the derivative, that's the alpha order derivative of x raised to the power of lambda. But, well, there are some restrictions here. Since the gamma function is only defined when the input is, like I said, when the input is not a negative integer and it is not 0, we don't want lambda plus 1 to be 0. So, and it should not be a negative integer. So to keep things simple, let's think about a case where the input is positive. Okay, so think of lambda minus alpha plus 1 being positive. But this case will cover this one up. Good. In other words, lambda should be greater than negative 1. So the power of x That is the power of the power function. The power there should be greater than -1 for this to make sense. But well, like I said, there are some holes on the negative axis. Every negative integer will give us trouble, so that will make the case complicated. So let's keep it simple by thinking of lambda being greater than -1. In other words, the power for the power function should be greater than -1. Okay, that's nice. So with that, we can think of any power function provided the power is greater than -1, and then for any order, okay, any positive order, we can use this definition for that. So this is the result that we get. So going back to our goal is to find this. Okay, so let's see what we can do with this result. So from this result, what can we do? So we say, suppose that the order, okay, we want the order to be pi, okay, the pi-th derivative. So suppose that the order is pi. Good. So suppose that alpha is equals to pi. Okay, good. So what happens? Well, that is the pi-th derivative with respect to x, okay, of, in this power function, x raised to the power of lambda, where lambda is greater than -1, will be, well, gamma of lambda plus 1 divided by gamma of lambda minus pi plus 1. Good. X raised to the power of lambda minus pi. So maybe let me use red for that. I haven't even thought of changing inks. Anyway, so this is pi. We just substituted. Okay, so that is the pi-th derivative of that. Okay, that's nice, isn't it? Good. So you can choose your values, that is your real numbers for lambda, given that lambda is greater than -1, and you will get particular solutions, that is particular derivatives. Okay, there are some things I'd like to talk about. Okay, as another very interesting case, we can also think of a case where the order, so we say suppose, that's another case, that's a case where the order is 1/2. So suppose the order is 1/2, that is alpha is equals to 1/2. What happens? So we'll have the half derivative, so you say the derivative raised to the power of 1/2, okay, of x raised to the power of 1/2 of this function x raised to the power of lambda. Well, this would be gamma of lambda plus 1 using the same definition divided by gamma of, now this is going to be -1/2 plus 1, that is from the inputting 1/2 for lambda, but that would just be gamma of -1/2 plus 1 is just +1/2. Good. And then we have x raised to the power of lambda minus 1/2. Okay, and you can, and you may want to think of this thing as a really simple case where the power of this x is just 1. So you think of lambda being 1. 1 is greater than -1, so it makes sense. And when we think of that, this is the results we're going to have. So I'm going to say, suppose that lambda is 1. Okay, so what we'll have will be that the half order derivative of x raised to the power of, well, lambda is 1. Good. This is equal to gamma of 1 plus 1, which is gamma of 2, divided by gamma of, well, 1 plus 1/2, that's 3/2. Oh, big trouble. Good. This is x raised to the power of, we subtract 1/2 from 1, that will be 1/2. That's just square root of x. Okay, so gamma of 2. Well, remember what I said here, that gamma of beta plus 1 is beta factorial. Today is going to be the same thing as, 2 will be gotten from 1 plus 1. Okay, that means we're going to have 1 factorial, which is just 1. So gamma of 2 is 1. That is easy. Now, gamma of 3/2. Well, I need to write it, maybe to remind or just to let you know, and you get used to it. Is that gamma of 3/2, okay, is the same thing as what? Square root of pi over 2. Well, we have a lot of pi's. Square root of pi over 2. Let me write it well for you to see. So this is square root of pi over 2. It's a very important result. Okay, great. We check out a video on this, gamma of 1/2 and then gamma of 3/2. Okay, that is from -1/2 factorial. Okay, so this right here is the result. So this, we can substitute that. That means we're going to have, in place of gamma of 3 over 2, we're going to have square root of pi over 2, which I can write as 2 over square root of pi. Then we have x raised to the power of that will be square root of x. Good. So in the end, what we have is 2 over square root of pi times square root of x, and this right here is the result when lambda is equals to 1 and then alpha is 1/2. But for our goal, this right here is it. Good. Okay, that's nice, isn't it? So you check out our video on what is negative 1/2 factorial, right? Okay, what if, maybe you may be asking, what if it's not a power function? What if maybe we have trigonometric functions? How can we find maybe half derivative of a trig function, okay, and something like that? Well, there is a very cool formula for that. I got it from we talk about Riemann fractional derivative, that's fractional calculus. Okay, so for a fractional order, this is the main result. So we have this to be the derivative. This is the notation for the derivative, that is d dx. Okay, but here we have an order, alpha order. Let's say our lower bound starts from a. Okay, good. We can still use it to define an indefinite integral anyway. So this is the function. So for any function x, such that the function is nice, and by nice, the function needs to satisfy some properties. And you look and check out for fractional derivatives. Okay, that is on the fractional calculus, and you're going to learn all of that. So this is gamma of, well, m minus alpha. I'm going to discuss what m stands for. This is the mth order derivative. M is actually an integer, but I'm going to explain what it means. This is the integral from, this is a, where a is the lower bound, like I explained, up to x of, let's rewrite our function, okay, in terms of a dummy variable. And this dummy variable is going to be tau. Let's use tau for that, divided by x minus tau, good, raised to the power of 1 plus alpha minus m, okay, minus m, good, okay, the tau, good, where this m, where this m means, where m is the least integer greater than alpha. In other words, m minus 1 is less than alpha, and alpha is less than or equal to m. That is, m is the least integer greater than or equal to alpha. Okay, so this right here is it. You can use this for any function, like I said, where the function is nice enough. By that I mean it satisfies the properties. You should check that out. We can use that. Now if we substitute, if you think of f as this function as a power function, okay, substitute in here and then do everything, you're going to get the same result, which is this result right here. And you can, yeah, so this was actually a nice approach anyway. Okay, thanks for watching. I hope you enjoyed the video. Please don't forget to check out the video on negative 1/2 factorial, and subscribe to my channel, and share the video with your friends. Thanks for watching.